Hello, Mr. Betts here. Let's take a look at an example where we're using that exponential growth model in the case of the population of a bacteria colony. So first thing I want you to understand is this growth can only be modeled with exponential growth for a certain period of time. And then eventually resources, food, whatever, are going to run out, space maybe. It can't keep growing exponentially. Otherwise, this colony would take over the world within a matter of a few days. But during some period, this exponential growth model is going to be a pretty good model. So remember the differential equation that we solved is this, which gives us the solution that looks like this. And what we're looking for in this problem, the number of bacteria initially in the colony is going to be y naught. I do want to point out this is not a calculator problem. This is one that we're going to be able to do entirely without. But usually these exponential growth problems, we're going to need a calculator to help us out. So there's two initial conditions, two data points that are given to us here. One is that there's 10,000 bacteria after 3 hours, one that there's 40,000 bacteria after 5 hours. So I'm going to use each of those to set up an equation. So we're going to have 10,000 equals y naught e to the k times 3. And then we're going to have 40,000 equals y naught e to the k times 5. Now, since we have two equations and two unknowns, the initial population and that growth constant k, we can solve this system of equations. It is possible to solve for k in one of them and plug it in for the other to find y naught. I actually think it's easier in this case to solve for y naught in both to solve for k and then use that k value to go back and solve for y naught in either one. So that's the process I'm going to take. So solving for y naught here, we're going to get y naught equals 10,000 over e to the 3k. And here we get y naught equals 40,000 over e to the 5k. So what we can do now, since we know what y naught is in both, we can set those equal to each other. So we get 10,000 over e to the 3k is equal to 40,000 over e to the 5k. And to solve this, essentially we can swap the e to the 5k and the 10,000. So if you think about if we're cross multiplying here to solve for k, we would be multiplying the 10,000 times the e to the 5k regardless of where those are, top left and bottom right. So e to the 5k over e to the 3k, which using rules for exponentials, that's just e to the 2k, is equal to 40,000 over 10,000, which is 4. Then we take the natural log of both sides. So natural log of e to the 2k is just 2k. And then divide by 2, and we get k equals the natural log of 4 over 2. And actually, I'm going to simplify that a little bit. So that's the same thing as the natural log of 4 to the 1/2 power. 4 to the 1/2 power is the square root of 4, which is 2. So this is just the natural log of 2. So k is the natural log of 2. So I'm going to take that now and substitute it into one of these two equations to find y naught. I'm going to choose the first one here just because it's got smaller numbers and it seems like it would be easier to work with, but either one will give us the same answer. So we get y naught is equal to 10,000 divided by e to the 3 natural log of 2, because we're plugging natural log of 2 in for k. 3 natural log of 2 is the same thing as the natural log of 2 to the 3rd power, which is the natural log of 8. Oops. So this is 10,000 over e to the natural log of 8. And e to the natural log of 8 is 8. So we get 10,000 over 8. So y naught is going to be 1,250 bacteria initially in that population.